Many physics concepts are present in our everyday lives without us really recognizing it. For example, the toaster, and why the redundant red color appears on hot items was a question the inventors of physics were trying to figure out. But today I am here to talk about work, another one of those undermined physics concepts. And I'm not talking about sitting at a 9 to 5 desk job type of work, but instead the measure of energy transfer that occurs when an object is moved over a distance. Work is a concept in physics that describes the transfer of energy from one object to another, or in other words, force times distance. Work can be positive or negative, depending on the direction of the force and the direction of the movement. It can also either add or remove energy from a system, but don't get that confused with the law of conservation of energy, as work does not create nor destroy it. Work is also measured in joules and has no time factor, for if it did, it would be considered power, which is a concept I'll talk about later. As explained earlier, work can be calculated, and I'll show you how, using the force parallel to distance equation. For the first problem, a cart is being pushed with a force of 50 newtons for a distance of 100 meters. How much work is done on the cart? Since we are provided force and distance, the most logical equation would be the work equals force parallel to distance equation, also considering the fact that the force and distance are traveling the same direction. When we plug in the numbers and do a little bit of multiplication, it is clear to see that 5,000 joules was the amount of work made on the cart. In the perfect world, force would always be parallel to distance. But this world is not perfect. So how do we calculate work then? Well, I'll show you. In this next problem, where we can assume our mass is 88 kilograms and the acceleration of gravity is 10 meters per second squared, how much work do we do when we climb a flight of stairs that is 2.5 meters high? So we are given mass, gravity, and height. How in the world are we going to find work with that? Well, there is another equation that we can use, which is work equals a change in energy. In this case, we are going to use gravitational potential energy, which is equal to mass times gravity times height. When we plug everything in, we get 2,200 newtons as our GPE. If we set the GPE at the bottom of the stairs equal to 0 and the GPE at the top of the stairs equal to 2,200, then we can calculate the difference in order to obtain the amount of work done, which is 2,200 joules of work. Now let's relate work to time. That is called power, which is the rate at which work is done. It is measured in watts, similar to a traditional light bulb that we are familiar with. And actually 1 watt equals 1 joule per second. The standard equation to calculate power is work over the change in time. With that being said, the work of a light bulb is not the same as the rated power of one. For example, a light bulb rated with 100 watts of power sits on for an hour. What is the work of the light bulb? Well, we know 100 watts is 100 joules per second, and 1 hour is 3,600 seconds. When we arrange the standard equation to solve for work, we get work is equal to power times time, in which we can get our final answer of 360,000 joules of work. Now let's try solving for power. In this next problem, a man is exerting a force of 30 newtons onto a sliding cabinet with negligible friction, causing it to move 1 meter in 30 seconds. What power is used? Since we are given force, which is 30 newtons, and velocity, which we can rewrite as 0.03 meters per second, we can solve for Newton meters per second with simple multiplication to get 1 Newton meter per second. And fun fact, 1 joule is equal to 1 Newton meter, which can then help us solve for watts since 1 joule per second is equal to 1 watt. Our final answer is 1 watt of power. Now it's time for everyone's favorite part of physics, the graphs. Work and power can be shown through graphs in various ways. The first way that power can be represented through graphs is through a force versus velocity graph. The area under the curve represents the work done, and since power is the rate at which work is done, the area under the curve is equal to power. And a way for work to be represented through a graph is in a power versus time graph, and since power is the rate at which work is done, the area under the curve of a power versus time graph represents the work done over that period of time. Thanks for watching. I hope you were able to learn a little bit more about work and power, when to use it, where to use it, and how to use it.